remember, in that it has something to do with differentiation. They like undo each other? No, I mean, not really. You need to think about what you actually mean by that. But that's what we're going to do. We're going to prove the fundamental theorem of calculus, which, if you recall, has like two statements. The first is if you have a continuous function and you define another function by the rule that big F of x is the integral up through x of f of t with respect to t, then the derivative of that is little f. So the integral gives you an antiderivative. The other version of the fundamental theorem of calculus says that if you happen to find a function which is an antiderivative for little f, then the integral of little f between two things is just given by evaluating that antiderivative. Right, that's like the almost final thing you do in calculus. So our goal today will be proving those theorems. And let's go ahead and begin by just remembering how it is that you define the integral. The Dirichlet integral is what we'll deal with. We could have done this just as well with the Riemann integral. So let's see. Now let's draw our definitions. So if I give you an interval and a finite collection of closed subintervals of that big interval, J1 through Jn, when is that collection called a subdivision of I? What things need to be true? Do those two purple intervals give you a subdivision of the white interval? Why not?
There's points missing.
Because there are points missing. Okay. So what if I do that, but also do that? Does those purple intervals give a subdivision of that white interval? No, because there's stuff in the purple that's not in white. So maybe there's like a set equality version of saying that? So one of the things that needs to be true for it to be a subdivision is if you take the union of all of the jk's, you need to get I. Well, okay, so that means that something like this has to happen. What if I include this yellow subinterval in addition to all of those purple ones? Is that a subdivision?
No.
Why not?
Because there are points that are in more than 2.
There are points that are in more than 2. So the other condition is basically that all of the intervals have to be disjoint, except that we can't have them all being disjoint. Sorry, that endpoint will be in 2 different purple intervals. So if you take I not equal to k, then ji intersect jk is at most 1 point. And that point will be one of the endpoints that would be a common endpoint of the 2 intervals. Let's let f be a bounded function. So I'm going to try to remember what the definition of the Dirichlet integral is. And so how did we define it? We defined it in terms of these upper and lower sums, which in turn were defined in terms of these little m's and big m's. So let's let f be a function, delta be a subdivision of I. Then f happens to be bounded on each of those j's because it was bounded on the whole I. Big M is defined to be, did we set big M to be the sup on the nth? Sup, which of course it better be, that's just the standard thing to call the capital. And I'll set L of j to be the length of the interval j, so the length of an interval is just the difference between its endpoints. The upper and lower Dirichlet sums are now given by, what was the formula we had for the upper Dirichlet sum?
The sums of the capital M of f j's multiplied by the length of j.
Yeah. And the lower Dirichlet sum was the same thing, but you used the lower numbers. F comma j, length of j. Finally, the upper and lower Darboux integrals. So the upper Darboux integral was supposed to be like the smallest of all of the upper bounds on how much area should be under the curve. So it should be the infima, because I don't really mean the smallest, there is no smallest one. I mean the infimum of them. The infimum of all of the, which ones give the upper bounds on the area under the curve? Yes, pluses. Same thing with lower integral. And if those two bounds happen to agree, we'll call the function Darboux integrable. And the Darboux integral will just be, well, that number which you now know must be the area under the curve. And a question was asked last time, if you have, so one of the things you guys proved, I think was assigned on Friday for homework? If you have two functions that just differ at like a single point, then they have the same Darboux integral. Maybe that's assigned today, I don't know. Well, we observed that, okay, so a function that has like a single discontinuity, like that's going to be Darboux integrable, because it's Darboux integrable there, it's Darboux integrable there, and then you just put them together. And it was asked last time, oh, well, what if you have like, so clearly you can get away with countably many discontinuities. And it was asked, well, what if you have countably many discontinuities? And in fact, there is a theorem, which is the Lebesgue condition for Riemann or equivalently Darboux integrability, which says that if the Lebesgue measure of the set of discontinuities is 0, then the function is Darboux integrable. So the reason I mention that is because I want you guys to do a final project or something. And if someone wants to like do a final project that introduces Lebesgue integration, that would be a good goal. Do enough measure theory to get that. Okay, cool. So tangent done. We have a definition. There's the integral. And before I prove the fundamental theorem of calculus, I'm going to prove another version of the mean value theorem, this time for integration. So here's a mean value theorem. So let's let f from a to b to r be a continuous function. Then there exists some c in the interior such that f of c is the average value of the function as defined by integration. That should be the average value of the function, right? Like add up all of the values and then divide by the number of values you took. That's not like what that means, but you can't do that because there are uncountably many numbers between a and b, but the integral is designed to deal with that. So let's prove that. Let's prove that fact. And the proof will be very easy as long as you allow me two facts about integrable functions. The first is if you have two integrable functions, f and g, and f is less than or equal to g, then the integral of f is less than or equal to the integral of g. So there's one of those. Let's maybe, did I have you guys do a proof of that one for homework? Okay. I knew there were like a bunch of properties of integrable functions that I did have you guys do, but there were also just a lot of properties of integrable functions, which all have kind of the same proof. I don't want to read those. So there's one, and the second is the integral of a constant is exactly what you know it should be. Did I have you guys do the integral of a constant? I did that one, right?
I think so.
Okay, so let's just take those two facts for granted, and let's prove the mean value theorem. So let's let f from a to b be a continuous function. Let's set mathcal I to be, well, the mean value of the function as given by integration. So I want to prove that there exists some number c such that f of c is equal to mathcal I. And this is a continuous function. So by the intermediate value theorem, there are like two cases, right? Either this function is always less than I, or the function is always bigger than I. Because the intermediate value theorem says that if this function is ever bigger than I and less than I somewhere else, then somewhere between it has to be equal to I. So that's how I'll try to approach it. So let's make that assertion clear for us. So if there exists two different numbers, u and v, with f of u less than I is less than f of v, then the IVT concludes that there is some c between u and v with f of c equal to math cal I. Well, let's just, in one, to really quickly make sense of why this means what done. So the theorem claims that there exists some number c between a and b with f of c equal to this thing that I said I equal to. So this is the c that I want. Is it clear why that c should be in the in the open interval from a to b? Yeah. Can you say like a few words about why?
Why C is in the closed interval from A to B?
Yeah.
Because C is between U and B, which are in that interval.
Yeah. And in fact, C is even C is in the open interval from U to B, I think.
Yep.
Right. The intermediate value theorem gives you something strictly between.
And it has to be that way, right? Because if it's a function, then it can't map to two outputs. F of A or F of U and C. Pretty different. I think.
Yeah, so I mean that does tell you automatically the U and V are definitely different, but that's not the issue with steak, right? So you know, let's just draw a picture. So you know that there's B, you know that there's some U and V in between them. You know that C is in there,
Okay.
so C has to be in there.
Okay.
So all I have to do is justify why U and V both exist. I'll proceed by contradiction. So let's suppose it is not the case that there exists two inputs U and V with f of U less than I is less than f of V. So let's suppose that isn't the case. Well, so let's try to massage around what that would mean. That would mean that there do not exist two inputs where f of U is less than V, f of U is less than I is less than f of V. So not there exists would be like a for all. And I'm saying there exist two different things. So there will be an or between two universal quantifiers. So either this function will always be less than I, or the function will always be greater than I. Like that's the right negation. So let's suppose, for the sake of contradiction, okay, so I'll do them one at a time. Let's just find why U exists. Suppose, for the sake of contradiction, that for all U in the interval from A to B, we have f of U bigger than I. Oh, because the IVT is perfectly happy if you have loose inequalities there. Okay, well, let's try to deal with that. So let's see, if f of U is always bigger than I, let's try to make sense of this. Then, by corollary 10, which is stated up here, the integral of the function f of x dx, how would it compare with the integral of the constant I?
Be great in that.
Be great. But the integral of I, well, that'll be like, oh, that's A upon B sub A upon B. Well, that's exactly B minus A times I. But look at the definition of A. What is B minus A times I?
Integral from A to B of f of x.
Oh, wait, so the integral from A to B of f of x dx is strictly greater than the integral from A to B of f of x dx. That seems like a contradiction. So there must be some u in the interval from a to b with f of u less than or equal to I. Do you think we could do something similar to come up with the existence of a v? Yeah, and that's all we need, because now we can appeal to the intermediate value theorem to complete the proof. And in doing this, there's a gap, because you need something a little bit better than that. So maybe I'll improve that statement just a little bit. So if f and g are both continuous, and f of x is strictly less than g of... Oh, you can't see that even a little bit.
That's better.
Yeah, well, the trouble is, like, it adjusts to lighting based on how much brightness is on the screen. But I'll just do it in this color pen. If f and g are continuous, and f of x is strictly less than g of x for all x, then the integral of f of x dx is strictly less than the integral of g of x dx. Well, kind of, you do need continuity a little bit in that. Cool. So now we have the mean value theorem for integration done. That's the main thing that I'll need in the proof of the fundamental theorem of calculus. So let's state the fundamental theorems and just see what happens. So let's let f from a to b be a continuous function. I'll define a function f from a to b to where by the rule that big F of x is the integral from a to x of f of t dt. Then I claim that the derivative of this function is exactly little f of x. Though maybe you'll notice that if you plug in like x equals a, I need to make sense of the integral from a to a. But a comma a isn't an interval, so the definitions that I made don't make sense. But I don't know, if you have a function that's only defined at one point, what should the area under that curve be?
0.
Because it's just like a line segment, it has no area. So I'll just set that to be 0. I'll establish another convention a little bit later on to make things a little bit stronger. The second version of the fundamental theorem, let's let little f be a continuous function and big F be a differentiable function satisfying that it's an antiderivative of that function little f. Then the integral from a to b of little f is just evaluate the antiderivative at the endpoints. So if you can find an antiderivative, then you can compute the area under the curve, and that's like 2/3 of the content of Calc 2. And then it's like coming up with formulas for antiderivatives. But all of those are just like remembering derivative formulas. So let's go through the proof of version 1 of the FTC. So let's let f from a to b to where be a continuous function. So something that's worth pointing out, since this function is integrable all the way from a to b, it's only integrable from a up to x. Was that one of the whole problems? I think it was one of the ones I was at least considering as the candidate homework problem. Okay, well, it does follow. You can use this idea of there exists a subdivision where s minus is pretty close to s plus. Because if you use a smaller subinterval, the difference between s plus and s minus will be even little more. You add up fewer things. So it's actually integrable, so it actually makes sense to say big F of x is the integral from a to x of little f of t dt. I don't need to put an overline or underline there. So I need to show that the derivative of f of x is f of x for all x in the interval from a to b. That's what my goal is. So here's what I'll do. I'll fix some x in the interval from a to b. And let's think about what I'll need to do. So what's the definition of the derivative? Let's kind of sketch it on the board before we do it. So if I want to prove that f prime of x is the same as little f of x, what's the limit statement of f? What's the limit definition of big F prime?
Limit as h goes to 0 of f of x plus h minus f of x all over h.
Let's look what's going on up there. So that's like the integral from a up to x plus h of f of x, f of t, dt, minus the integral from a to x of little f of t, dt. I guess on your Calc 1 brains, what should that integral is the same as what? I could write it as a different integral.
Limit or integral from x to x plus h.
So this thing that I want to take the limit of, so this is just scratch block. This is the same thing as the integral from x to x plus h. I guess here I'm assuming that h is positive. Otherwise, those are in the wrong order, so I'll need to make sense of what it means for things to be in the wrong order, which isn't so bad. Divided by the length of that integral. But what does the mean value theorem for integrals tell you about that?
There exists some c in the range x to x plus h that takes on that value.
Nice. So this is saying I want to compute this where h is really, really close to 0. But this says that's the same thing as little f of c, where c is between x and something that's x plus something that's close to 0. So that little c, what can you tell me it's close to?
X.
X. And if c is close to x and f is continuous, then what is f of c close to?
X.
F of x. So the limit we wanted to compute is really close to f of x. That's convincing, right? Now you just have to make it into a proof. Some of the things will be clearer if instead I use like that notation instead. So I'll use that notation for the derivative instead of the h definition. So first let's so it looks like I want to get such a study what happens. So I want to show that f prime of x is equal to f of x, so I'll fix some x in the closed interval from a to b. I'll consider any epsilon bigger than 0. And it looks like this is the thing that I really need to be close to x. So let's use continuity. So because f is continuous at x, there exists some delta such that for every c in the interval from a to b, if the absolute value of x minus c is less than delta, then the difference between f of x and f of c is less than epsilon. And I guess here it's confusing because like the x and c have like the opposite job as what you might have wanted. X was the thing that we fixed, and the c is the thing that's just pretty close to x. But that's okay, right? Have I actually correctly written down the definition of continuity? Okay. Cool. And like I said, I'm going to try to get away with this like instead y going to x instead of h going to 0 definition. So let's consider any y in the closed interval from a to b. Let's assume that the absolute value of y minus x is less than delta. Then what is it that I need to show? So I'll eventually want to show that the integral, no, there's no integrals. I want absolute value of f of x minus f of y all over x minus y. I need that to be close to f of x, little f of x. So I need that to be less than epsilon. That makes sense? Because that's the thing which I claim is the derivative, so let's just try to do it. So let's suppose for the moment that y is less than x. We'll do the other way in a moment, soon. Well then, let's write down what this difference is. What that sum is. So that's like the integral from a to x of f of t dt, because that's what f of x is, plus the integral from x to y of f of t dt. And so, right, so that's the integral from a to x plus the integral from x to y. That should add up to the integral from a to y, which is the same thing as big F of y. Okay, cool. So in particular, big F of y minus big F of x is the integral from x to y of f of t dt. Happy enough? By the mean value theorem for integration, that's what theorem 1 in this note pack is, there is some c in between x and y such that f of c is the same thing as the integral from x to y of little f of x dx divided by y minus x. Oh, neat, but that numerator is like exactly what f of y minus f of x is. So f of y minus f of x is exactly the same as little f of c times y minus x. Everyone with me? And maybe the last thing to point out, c is somewhere between x and y. Let's draw a picture. There's x, there's y, there's c. So how does the distance from x to c compare with the distance from x to y? It's less than. And by assumption, how big is the difference between x and y? Less than delta. Cool, so the absolute value of x minus c is less than delta. So, well, maybe we'll even just do it slightly, well. Because the absolute value of x minus c is less than delta, what can you conclude by our choice of delta? That, right? So let's put this all together. So absolute value of f of x minus f of y, all over x minus y minus f of x, is equal to, let's see, f of x minus f of y is the same thing as f of c times y minus x. Oh, they're in the wrong order. Well, like it is actually the same if I write them in the opposite order, so that's just fine. So that means that this is little f of c times y minus x all over y minus x minus little f of x. Okay, but that's exactly the same as absolute value of f of c minus f of x. Nice. That's less than epsilon. Have we just succeeded in showing that for every epsilon bigger than 0, and for every x in the domain, there exists a delta, so that if the absolute value of x minus y is less than delta, then the difference between the difference you need to be close to something to compute the derivative and the thing we said the derivative, did we get that to be less than epsilon? So this is a proof of the limit statement we needed. But we only did it in the case that x is less than y. What do you think would be different if we instead took the case that y is less than x?
Switch all the x's and y's.
We'd switch all the x's and y's, and because we only had a convention what the integral means from a smaller number to a bigger number, those would be like opposites. But it would be the same proof. Therefore, what have we shown? We've shown, well, How do people feel about that? That go okay? Good. Okay, so in order to prove the second version, which, let's write it down. Oh, it's written here. If little f is a continuous function and big F is a differentiable function satisfying the derivative is little f of x, then the integral from a to b of f of x is exactly f of b minus f of a. So there's one result that I'll need before I can prove that, and that is something which, well, seems pretty obvious and indeed won't be hard to show. It's just something about derivatives. So let's let f from a to b to r be a continuous function. Let it be differentiable on the open interval from a to b. And suppose that the derivative is 0 for every x in the open interval from a to b. So what do you think the conclusion should be? What sort of functions should have 0 derivative? Constant functions, right? And that's all that this is. It follows then for every x in the interval from a to b that f of x is the same as f of a, but notice f of a is a constant in x. So this function is a constant function. And the proof is just another application of the mean value theorem, which now you'll notice I abbreviated it as MVT. It's not because it's the mean value theorem, it's because it's the most valuable theorem. I think that got exactly as much chuckle as it dissolved. Is that even where I have it? Oh no, that joke was supposed to appear in a different note packet. Damn. So let's suppose that you have a continuous function which is differentiable on the open interval from a to b. And let's suppose that f prime of c is equal to 0 for every c in the open interval from a to b. I've made a choice of calling this variable c because I'm going to appeal to the mean value theorem. And the thing that comes out of the mean value theorem is called c. So I need to show that f of x is equal to f of a for everything in that interval. So let's consider any x in the interval from a to b. If x is equal to a, then are we already done? If x is equal to a, then what is f of x equal to? F of a? Is that what we wanted to show? Yeah, so there's nothing to do. Because this is a function. It's not allowed to have two different values at a single input. So now let's consider any x in the closed interval from a to b other than a itself. Let's convince ourselves that the mean value theorem actually holds on the closed interval from a to x. Is it clear that this function is continuous on the interval from a to x? Yeah, because it's continuous on a bigger interval. You can restrict domains and you still get continuous functions. Is it clear that this function is differentiable on the open interval from a to x? Yes, for the same reason. So you can appeal to the mean value theorem on the interval from a to x. So there should exist some c between a and x such that what happens? And here I guess I mean the mean value theorem for differentiation, not integration. What does the mean value theorem say? There should exist some c between a and b
such that f of c is less than f of x, and then f of c is also greater than f of a. Is that the right theorem?
Nope, that's like what it would mean. If we could do, you'd say that if a single, like an increasing function.
Oh, okay.
Yes, that's something like the intermediate.
F of c would equal the mean value.
Yeah, f of, well, f prime of c. Right, this is why I want to appeal to the mean value theorem for differentiation.
Oh, okay, yeah.
So the mean value theorem says that there exists some c such that f prime of c is equal to the average rate of change of the function on the interval from a to x. What's the average rate of change of the function from a to x? Let's draw a picture of the mean value theorem. right, the mean value theorem says if you have some continuous function, then the slope of that line is the average rate of change. The mean value theorem says there exists at least one point where that slope is the same as this slope. So this has slope f prime of c. What's the slope of that line? So x equals a. So it says that there exists some c such that f prime of c is f of x minus f of a all over x minus a. Wait, well, what is f prime of c? By assumption in the theorem. 0, right? So that means that this thing has to equal 0. So f of x minus f of a all over x minus a is equal to 0. So what can you conclude? That wasn't so bad, I hope. And with that, let's prove the fundamental theorem of calculus. So somehow what that says, so here's how we'll use that theorem. I'll use that theorem to say, so on the one hand, let's suppose that I have this. So let's let little f from a to b be a continuous function. Let's let big F be a differentiable function satisfying f prime of x is equal to f of x. I would like to show that the integral from a to b of f of t dt is the same thing as f of b minus f of a. So let's look at that formula, and let's let these parameters be functions, be a variable. Then I get a function on either side, right? And if you take the formula on the left-hand side and you differentiate it, what do you wind up getting? Well, that's the fundamental theorem of calculus version 1, right? So if you differentiate this, well, in this picture it looks like differentiation with respect to b. You'll get just little f of b minus little f of a. And then you differentiate this, and you'll wind up getting the same quantity. So let's explore this. So let's let big G from a to b be defined by g of x is equal to the integral from a to x of little f of t dt by the FTC version 1. Tell me, what is g prime of x? Possibly by looking back at the statement of the fundamental theorem of calculus version 1 that we just proved. Yeah, little f of x, right? On the other hand, what do I know about the derivative of big F? By assumption, what is the derivative of big F? Little f. So big F and big G have the same derivative. So that means that big F of x, big F minus big G, the derivative of that should be big F prime of x minus big G prime of x. And what is big F minus big G? What big F prime minus big G prime? 0, because they're the same. So by proposition 4, what can I conclude about big F minus big G? What type of function is it? Constant. And in fact, I can do a little bit better than that. That should be the same thing as big F of A minus big G of A. I don't want to plug in x equals a. That won't tell me anything. Let's plug in x equals b and see what we get. So what will I get? I'll conclude that big F of b minus big G of b is equal to big F of A minus big G of A. So that means that f of b minus f of a is the same thing as g of b minus g of a. And maybe that's not as we claim just yet, but we're pretty close. So let's see. Our eventual goal is big F of b minus big F of a is the integral from a to b. So that's this quantity. What can you tell me about g of b minus g of a? Let's use the definition of g. So, by the definition of g, what do we have? We have f of b minus f of a is equal to, g is by definition an integral. The integral from a to b of f of x dx minus the integral from a to a of f of x dx. But what's just our standard convention? What is the integral from a to a of f of x dx?
0.
0, so I'll just drop that. That gives me the integral from a to b of little f of x dx. That proof makes sense? And you'll notice that I didn't have to write down any Darboux sums to do this. I basically just needed a few abstract facts about integration. And so there's another perspective you could have on what the integral should mean. It should be an operator from the space of continuous functions to the space of continuous functions satisfying some axioms. So you could write down a purely axiomatic approach to integration. And then the downside would be that you would forget entirely that integration is the area underneath the curve, which is maybe important. And in fact, let's notice a corollary that we have. Let's let little f from a to b, from ab to r to be a continuous function. Then I claim that there exists a function whose derivative is exactly little f of x. And so it's an existential thing. What function is it that I want? How about the integral? Which is maybe the opposite of the way that from Calc 1 you're used to using these theorems. You're used to finding an antiderivative by doing tricks, and then saying that antiderivative computes the area. But the function given by the area under the curve, you can just understand. You might not be able to compute it on the nose, but who cares? You can understand it more or less. That is the antiderivative and antiderivative. How do people feel about that? Pretty okay? Cool. So I think that I'll want to, for the sake of the next lecture, want to improve it just a little bit. Let's let f be a continuous function on an open interval from a to b. So I don't know that the function is even defined at a or b. Then I'll fix some c in the interior. I'll define a function big F from a to b to r. By the rule, big F of x is the integral from c to x of f of t dt. Then big F prime is the same thing as little f. But you'll notice that there's a problem in that. Is that x guaranteed to be bigger than c? No. So I'll need to make sense of what the integral from 2 to 1 means. And you remember exactly the convention from Calc 2. If I integrate in the long order, I'll just look the bounds of integration, stick a negative sign up front. And with that convention, this theorem holds. And let's just kind of sketch the proof. So let's let f from a to b to r be a continuous function. Let's let c be a thing in the open interval between. Let's define a function by this rule with the convention that if x and c are the same, I'll set d0. If x is less than c, then I'll set it to be negative the interval from x to c. When x is bigger than c, I can just use the fundamental theorem of calculus that we've already proven, right? So that's just fine. When x is less than c, here's what I'll do. I'll let a0 be some constant quantity that's strictly between a and x. Let's kind of draw a picture on it. So there's a. So I want it to not be continuous or even bounded close to a. So that's going to remind me that I can't actually compute f of a. I have some x less than c. I'll fix some a0 that's less than x. Then instead of trying to directly think about the integral that I want to think about, the integral from x to c, instead let's think about integrating starting at a0. So big F of y, which right now is by definition the integral from y to c of f of t dt. Well, that's the same thing as I could integrate from a0 all the way to c, but then subtract off the integral from a0 to y. Right? Those are the same? Well, neat. So now I just need to take the derivative of that when y is, and then plug in y equals x. Are there any y's in this piece? Nope. So what's the derivative of that piece? 0. By the fundamental theorem of calculus, what's the derivative of that piece?
Y.
Little f of y, and now plug in y equals x, and you're done. Cool. How do people feel about this? Does this go okay? Nice. And then there are some homework assigned today. There's also the benchmark that I just gave you guys. I don't know. I feel like Monday is probably a good target date to give me the benchmark. Well, you guys know how the benchmark works already. Right? That's not a sharp deadline because the only real sharp deadline is the last day of the semester. But they'll give it to me, I'll mark it up, I'll give it back, they'll give it back to me with those things corrected, and that process will iterate until you get 100% and a sticker.
I don't think we got stickers last week. I don't think that was part of the protocol.
Oh yeah, that's right. I couldn't find my stickers at the beginning of the semester last time, so I just didn't give out any stickers.
So now I think we understand.
Okay, now you understand. Although technically they might not be stickers.
Okay.